Good morning, mathematicians. Hope you're all doing well. Hope you're all proving theorems. You better be. Better be proving them right now. You better have been mid-proof and then looked up from your screen to see the live stream. I'm, of course, constantly proving
proven theorems
in my mind every moment of every day. Am I proving worthwhile theorems? Am I proving good theorems? No, I didn't say that. I didn't say that I wasn't producing garbage math. I simply said that I was producing math. What to yap about today? Who knows? Who knows? I could keep going with Lie algebra stuff, but I think I've exhausted a lot of what I can do just straight from memory, and it's very possible that I will make a series on that. There seemed to be some interest. I was hoping I would get more comments from what people wanted to see. I didn't get a lot, but the few that I got, a large percentage was interested in learning more about Lie theory and, I guess, classification of Lie algebras. So that would be a fun thing to do. It was very possible I might do a more formal series on it. Make pre-recorded videos and stuff. Yeah. Not a lot of us. I remember when I was wait a second, lawn, or is it just a weird Canadian thing? How else do people say lawn? Now every time I say lawn, LNX? Oh, I see. Why not? It's not like you're doing anything better? What do you mean, Deepak? Yeah, how many of you guys study the elements? So I remember there was this guy. Actually, I wish I had stayed in contact with him, because we did have interesting mathematical and philosophical discussions, and I'd love to revisit some of the discussions we had now that I have more experience and understanding. But one thing that he was adamant about, he was like, all mathematicians should read the elements. As a certain part of me that agrees with him, because he was like, you need to know where you came from. This is the foundations of this is the foundational text of all of modern math, basically. This is really a huge step forward, and it informs our concept of space and geometry to this day. Yeah, and I remember one of the things. So he was really interested in this concept of how we think about geometry in terms of points and stuff, and he was questioning whether we even should be doing that, and he was saying we just accept this way of thinking from Riemann and stuff as well. And I knew back then a little bit about pointless topology and functor of points perspectives, but not enough to have a meaningful conversation. So that's one of the possible ways, one of the things I'd love to talk to him more about. But I tried finding, I couldn't find his email in my old emails, and so I have no idea where he is now. Also, with homotopy type theory, this introduces a whole interesting new philosophy into mathematics. Confusion about differential forms and exterior products. Yeah, me too. Physics research assistant, working on a derivation that involves a lot of tensor calculus, and I'm really confused. It's my understanding that the tensors I'm working with are all one forms. Okay. Well, then you don't need to worry about wedges. I don't know if the resulting tensors from performing exterior products on these tensors remain one forms. Well, they don't. Not if you're taking. Can I explain what a tensor is? Oh, well. Yeah, I can give you a short explanation today, but I don't know if you know, but I have a whole series on tensors. I have an entire series. It's unfinished, and I don't know when I'm gonna get around to finishing it. But if you're unsatisfied with the quick explanation I give you now today, I've got like at least 10 videos on it. But video 1 gives you the overview of exactly what a tensor is. So, Tensor Cookbook. I haven't heard of it, but I trust opinions coming from chat. If chat says it, then I agree. Now, here's a question. Why isn't my writing pad working? Riddle me this. Okay, here we go. So we have tensors. I mean, this is already kind of a loaded term because there's tensors. I mean, the point of my series was to explain the sort of joke definition, but not really that much of a joke. Is that tensors are something that transforms like a tensor. That's the physicist definition. It's actually not as stupid and silly as it maybe seems. And maybe I'll explain this in a second. But the physicist tensor is, in some sense, I mean, you know, for practical purposes, you might ignore aspects of the rigorous definition. But that is technically what the physicist definition of a tensor is. Really has to do with relies on the concept of tensor products of vector bundles, and that in turn is sort of a generalization of the ordinary tensor product of vector spaces, and that's maybe where we should start, is the formal construction of this thing. Amazing greeting there, Dason. Amazing greeting. That's fantastic. You saw my post today. What do you think of the idea of computing examples of the 6 operations functors on a morphism of sheaves, direct image, inverse image, etc.? Yeah, actually, I would like to do something with that at some point. I mean, in the back of my head, there's like maybe easy content, but extremely niche content I could make regarding my research. And like, there's a fun computation with perverse sheaves that basically involves a whole bunch of adjunction pushing. So you're just using adjunctions of these 6 operations in the derived category. So yeah, and it's definitely been on my mind. And then also there's like you know, showing the you know, quasi-coherent sheaves on spec A. That this, you know, is equivalent to A modules, and then showing that like the various different I'm going to come back to tensor products in a second, don't worry. But that there's various different you know, commuting functors, and that like extension and restriction of scalars, you know, commutes with like push forwards and pullbacks over here. So that's something where like eventually will be some sort of intersection. Maybe I'll make some affine schemes videos, and then that'll merge with the sheaf series. But that's like a ways off. That's kind of like a ways off because I'd really like to slowly build that up properly. So those are some things that are maybe coming very slowly down the line. Do some singularity resolution like for T4 mod Z2 and then blowing it up to make a K3 surface. Definitely can't do that live on, I can't just pull that out of nowhere. I don't know. I'd have to go look up how to do it. I'm not that much of an algebraic geometer, to be honest. But let's get back to tensor products. Hello, Arcturus. Let's get back to tensor products. So what is a tensor product? So let's start with the most simple, sort of naive interpretation of what a tensor product of vector space is. So keeping in mind that there's some work to do to go from tensor products of. So again, you can take a very loose intuitive approach to strictly get there for physics. But if we want to do things a little more rigorously and completely mathematically, there's sort of a few complicated steps here. First, tensor products of vector spaces, then tensor products of vector bundles, and then we can explain why this definition isn't such a crazy definition. So a tensor product of vector spaces, let me give you the following super intuitive, well, I don't know, intuitive, but suppose you have one vector space with two, which is dimension 2. So the vector space is isomorphic to R2, say a real vector space. And we have another vector space with a basis v1, v2, v3, and that is, so it'd be isomorphic to R3. Now, maybe you know about the direct sum of vector spaces, where you just, are allowed to put any vectors in the first coordinate, any vectors in the second coordinate, and overall, this would be isomorphic to R5 as a vector space. So in other words, more generally, if you have a direct sum of vector spaces, the dimension just becomes the sum of the dimension. Okay, so there's some sort of arithmetic of vector space dimensions going on here. And you might wonder, what other are there ways to create are there other vector space operations that correspond to some sort of arithmetic condition? And indeed, this is the case for the tensor product. So the tensor product, in this case, this is not a rigorous formal definition, but let me just tell you what a basis of this tensor product would look like. So we can construct it out of our bases above. It would be U1 tensor V1, U1 tensor V2, U1 tensor V3, U2 tensor V1, U2 tensor V2, and U2 tensor V3, right? So that is that would be a basis. So notice it would then be 6-dimensional. So in particular, the dimension of this, right? In general, the dimension of a tensor product should be the product of the dimensions of the individual spaces. Since the topic is tensor products and vector spaces, you just finished a linear algebra course covering up to Jordan forms. What would be the next step, be it books or something else? As your name says. That is a good question. Where do you go in terms of linear algebra? What's the next step after Jordan forms? I mean, it kind of depends on what direction you ultimately want to head in, right? I mean, one possible thing, like, in what generality did you cover Jordan forms? Because one thing you could do is then start talking about modules, and then you could sort of redo the whole theory of Jordan forms, but through the lens of the classification of modules over a PID. And that is a really cool thing. Yeah. Where else to go? I mean, the other, yeah, you could also go to matrix analysis, which I know nothing about. I don't know, Super Baron, if you've got references for matrix analysis. You could dive into some classical theory of Lie algebras. And there's some basic theorems there that you could use. And then before even going on to the crazy representation theory, actually you might need a bit of representation theory before you do this, but there's a whole very interesting study of nilpotent orbits. Okay, now I'm getting way like niche but probably if you want to go in an abstract algebra route, do modules over a PID. But also matrix analysis, which I know nothing about. You'll have to ask Super Baron for references. Check that out. Does one need an advisor to do research in math, or can self-study get you far enough to do meaningful contributions? It is very unlikely that you will be able to get there just through self-study. It is, I will say, almost certain that you need that you will need a supervisor and some sort of rigorous academic study for a number of reasons. So first off, I mean, okay, the thing is, there are easier things out there. Like, there are exceptions, right? So one exception, not this is the only one, but one exception that comes to mind is, like, there's this guy, Aubrey de Grey, who's into, like, life extension stuff and longevity science. He has some foundation dedicated to that. But, okay, he is not, strictly speaking, a mathematician. He does have a publication in, I guess, like, combinatorics that has something to do with, like, the coloring number of the plane. But instead of, like, it's not the four-color theorem, but it's some variant where you consider distances. Anyways, but, I mean, he does have a PhD in computer science. So he does have quite a bit of formal training in, academic rigor in the sciences. There are people, for example, Marjorie Rice, who Bonch, did you mean Banach was outside of academia? Yeah. Yeah. Oh, I didn't know that, actually. Actually, I sort of knew that. Yeah, because there's this story. I can't remember who discovered Banach. Was it Banach? Yeah, but there's some story with one of those guys where he was, like, walking in a garden and he overheard someone talking about Lebesgue theory, which was, like, breaking mathematics. That was brand new mathematics at the time. And he was like, what the hell is going on? He's like, who the hell is this crazy person talking about this? And then, yeah, that's how we kind of discovered him. So, it can happen, and I would say that's situations like that are also less likely nowadays in some sense. Well, mind you, I'm starting to, because I've also met some people who have done quite a bit of impressive work with self-study. Certainly, I know people and am currently in contact with people who have done very impressive things with self-study. But then to go from, like, let's say, yeah, producing a paper, then going on to producing a paper, that is also going to be very hard without some sort of supervision or guidance, because you need to, it's one thing to teach yourself things from textbooks, but it's another thing to understand what matters in a field, what people are interested in, and how to then take those results and how to write a good mathematics paper, and communicate that clearly. Yeah, Busy Beaver also true. Yeah, there was recent. There was a recent update. This is probably the most recent example of this happening. Yeah, the people. There was some like Discord server group made a bunch of progress on a new big result about the Busy Beaver problem. They figured out something about the next Busy Beaver number or something like that. So all of that to say is like it's not impossible. It's not impossible, but it's also, however, a couple from just proved a group theory theorem, and it took 25 years. Yeah, interesting. Yeah. Yeah, so I mean it's not impossible, but it's also it's so much easier if you're in academia, right? Because um it's also a matter of like having the community around you of learning, and also like having a supervisor is able to shortcut you into the from Germany. I'll have to look up that story. um yeah. So, anyways, I'm just yapping now, but as you can see, Super Barons produced a lot of examples, so it's definitely not impossible. Um, but it's if you can at least what would help things probably is if at least you can find some way to engage with the academic community so that you can get feedback as you're going, because if you don't have people to give you feedback on what you're doing, it can be difficult to know when and if you're going wrong, and so it's good to have that constant source of feedback. But that's also easier than ever now, right? There's all sorts of online spaces where professional mathematicians are hanging out, and you can, interact with people on those levels. So, yeah, yeah. Hello, Nikolai. So maybe I'll go back to yapping about this Tensor product. Of course, there's more. Hassan, if you got more questions, or anyone more questions about stuff, in chat, let me know. So that's the basic rundown on Tensor products. Could I help you with a problem you had on your test recently? Possibly. You could try dropping it in chat. This is a great time for me to advertise again that I do tutoring sessions. It's not cheap necessarily, but because I feel like my time is worth more money these days. But just reminding y'all. Watching a talk by Dustin Clausen this morning. Didn't say it, but implied that function spaces and analysis can be seen as some kind of ringed spaces. Crazy how learning sheaves opens the door to many definitions or many things. Yeah, sheaves are taken over. How do you prove that I minus A is invertible, where A is an n by n matrix, and I is the identity matrix of the same size? Well, that will not be true in general. In particular, if A is equal to I, that will not be true in general. And there exists an M such that A to the M is the zero matrix. It is not X a zero matrix? No. Okay, so we're supposing, So we're saying a to the m is 0 for some m, and we want to show that a minus I is invertible, or the other way around. Not that it matters. Potato Picasso. Oh, yeah, it was written as I minus a. Prove I minus a is invertible. Interesting. Well, probably what I would want to do is maybe try and cook up some kind of explicit inverse, right? So I'm imagining it's for some m. So m and every m greater. I'm not sure I understand. I mean, yeah, certainly if a to the m is 0, then for all for everything greater than m, that exponent will be 0. But then, so here's what I'm thinking. Because so we've got this term, we would like to multiply it. Like I want to multiply this by some matrix and try and get the identity matrix, right? And somehow I need to use this, right? So if I could like somehow factor out some sort of term or something, right? And so if I could somehow make like two terms appear, and maybe two terms that differ by like a power of a, for example. So maybe if there was, I don't know, if this was like a to the m minus 1, as an example, then maybe like this would factor into both of these terms, something like this. Newman series? I have no idea what a Newman series is. Hello, Fimno. So, with that in mind, I'm thinking about something like, if we had a to the m being 0, maybe we could subtract a from both sides, or maybe even, I guess maybe subtract a minus 1 from both sides. Maybe this isn't helping us. But let's not get dissuaded just yet. Induction on M? Possibly. I'm going to factor out a minus a to the m minus 1 here, and we'd be left with a minus I equals this. Yeah, that's not quite what we want just yet. Yeah, maybe we could try induction. But the thing is, you're probably right, actually. That's probably the best way to get it done. But I think, it's always better to avoid induction proofs if possible. Because induction is a very good tool. It will get the job done. But I feel that in many cases, induction is not very insightful. That is, it doesn't give you as much of an understanding as to why something is true. If the norm of the matrix is less than 1, I think that's probably overcomplicating things. I think that is probably overcomplicating things. Hello, Lubna. Could you assume it is not invertible, so that the determinant has to be 0 and has to be a not equal to 0? I'm not sure the approach you're suggesting there. And then proved by contradiction? Possibly. Possibly. Oh, well, thank you, Lubna. Thank you. Let's try. We could do by induction. That's maybe not a bad idea. And actually, you know what? Now that I'm starting to think about it, it could possibly give us some insight, which is something that induction normally doesn't. So let's suppose. Well, I suppose m can't be 0, right? So suppose m is equal to 1. Of course, if m was 0, a would be a to the m would be I, and definitely I minus I is not 0. So suppose m is equal to 1. Thus, a to the m is equal to 0. Sorry, a to the m 0 equal a to the m equal a to the 1, which is just a. That implies thank you, Lubna, for the words of inspiration. And so, of course, I minus a is just I minus 0, which is I, certainly invertible. Okay, let's just do the m equals 2 case. Let's just do the m equals 2 case, and see if that works. Assuming, of course, you know, we'll when I say m equals 2, I'm assuming that this is the minimal m that works, because again, like it was pointed out, all of the higher exponents would also work. Make most of brain, which is a gift from the Almighty God. Well, I will make the most of my brain. So what are we saying here? Okay, so let's investigate. So we've got I minus a. We want to try and show that this is invertible. Okay, here's something we could do to make a power up here. We could try squaring this thing. So, yeah, Lubna, such a lovely supporter, indeed. This is a question about eigenvalues. Since A is nilpotent, A has only 0 as an eigenvalue. Right. If I minus A isn't invertible, then that has a non-zero solution, which means I has another eigenvalue. Don't make the most of my coffee so the stream is longer. Well, actually, I have a tutoring session scheduled for 8, so that is as long as it's going to go. We're gonna end a bit before that. No, I think actually answer. Also, the binomial theorem doesn't really work here because the multiplication's not commutative. Well, okay. In this, I guess the I's and the A's, I guess it does work out here. Sorry, it does work out because we've got the just the identity matrix. Interesting. But yeah, it's actually yeah, I think has the right solution here is to use eigenvalues. I was thinking before that one could use something about the fact that A is nilpotent, but yeah, I was just thinking of the right way to phrase it. Bézou's identity? Huh? I'm not sure how that's going to be helpful here. I suppose in this case, we have what? That a squared is equal to 0. Uh, and then, yeah, not so clear. Not so clear how to proceed. Although maybe something can be said. But I think this eigenvalue way is probably the better approach, right? Yeah. So, right. If this is equal to 0, implies all eigenvalues 0. If I minus a isn't invertible, then this has a non-zero solution, right? So it has a non-zero solution. Right. And then I suppose that, right. But if I minus a isn't invertible, why does this mean that a has another eigenvalue, though? Oh, because, right. Because then if we expand this out, we get x minus ax. In other words, a has an eigenvalue of 1. Right. No, yeah, has a non-zero 1 eigenvector. Yeah. Nicholas, I'm not sure about your comment here. You say sum of eigenvalues equals the determinant. Yeah, that's not quite correct. Fantastic. Okay, we did it. Well, actually, did it. All credit goes to So where were we? Before that question. So whoever asked about tensor products originally, where are you? I wonder if you're still in chat. Well, mind you, oh, you are still in chat. I see. Well, if we don't, we're probably not going to say that much more about it today. But probably not going to say that much more about it today. However, I did mention that I have a whole series on tensor products. So maybe that'll help you. So you have this like rough intuitive idea. There's two ways to formulate it. Let me just quickly say, I've assumed. I'm going to say one other thing about it because I construct like a very formal definition using quotients from the in the case of modules. But another possible definition for the tensor product of two spaces is to define it to be the set of all bilinear maps from just the. So say we're doing real spaces. You can form it to be, you can define it, this is maybe less common, I would say, but you can define it to be the space of all bilinear functions out of the Cartesian product into R. And if you go watch those videos, you'll see why that coincides. But Alexandros is saying that I've assumed we're working in an algebraically closed field. Is that true? Yeah, maybe there's something weird going on here with the mini, like, you mean, is it somewhere here? Because I'm assuming some theorem about minimal polynomials. I said that I was going to read some papers live. Is that still your plan? Did I say that? It'd be if the chat can share recommend papers. Yeah, definitely. I mean, please share if you want me to talk about to go through papers live. I guess send me some paper recommendations. should that really be something I do live though? Because I mean, they'll just be me like staring at a paper. Like it takes a lot of time and effort to read a paper, um, even a relatively nice one. So I did actually send. Someone did ask in a comment about reviewing nice papers. Um, uh, so I did set aside one paper based on that comment. But maybe I'll do it. I mean, if that's what you guys want. But I just feel like live videos going through papers aren't like so interesting. I guess I could just read things out loud and explain my thinking. Wow, that's really brutally exposing myself there. Putting out my brain power for everyone to see, and to be like, wow, this guy's slow. But maybe some people think I'm fast too, so it'll balance out. I don't know. Be very careful of the book on tensors. There are some subtle errors in definitions. Look up the Matrix cookbook for explanation. Yeah. Do you have a video on your drawing tablet? I don't. I don't. It's I can just tell you it's a Wacom tablet. It's cheap, and it does all the things I need it to do, which is not a lot, but it's awesome. Some papers from Hilbert Nether revolutionizing algebra. Yeah, I've thought about that. I've thought about going through classic papers. That would be fun. Once more, you think at some point you saw either your video or some other video category theory. Which would you suggest as a nice resource for picking it up? McLean? I would not recommend McLean. Oh, guys, I have to go. I've got a tutoring session in 5 minutes. I would not recommend McLean. I mean, it's a great reference book, but to learn from, I would suggest either. I haven't read Emily Reel's Categories in Context, but lots of people like it. Also, Tom Leinster has a free PDF. I don't know what OSU is, so I don't play it. I think the only game I play these days is chess. Actually, I played through The Last of Us Part 1 with my homeboy recently. Notion of a sheaf and connects algebraic geometry and maybe differential geometry. Yeah. Well, I would go look at Leinster's notes or watch my video on sheaves. Anyways, I'm going to end it there. Gang. So, time to go prove some theorems about eigenvalues. Figure out where I made the assumption of algebraic closedness and tell me in stream tomorrow.